The National Electrical Code, or NEC, provides specific guidelines for grounding electrical systems, including those involving programmable logic controllers, or PLCs, and Ethernet communication. When dealing with Ethernet communication problems between PLC located in different panels, it is crucial to adhere to the NEC grounding rules to avoid creating ground loops and to ensure electrical safety. Section 250.54, Equipment Grounding, specifies that equipment grounding conductors shall be connected to the system grounded conductor or grounding electrode conductor at the service, at each panel board or similar distribution point, and at each motor control center. This section effectively prohibits the use of separate ground rods for individual panels. Instead, it emphasizes the importance of a unified grounding system. Section 250.24, Connection to grounding electrode system, further reinforces this concept, stating that the grounding electrode system shall be connected to the equipment grounding conductor at any accessible location inside or outside the building. This section underscores the need for a solid grounding system, as opposed to relying on multiple ground rods. Section 408.15, Equipment Grounding Conductors for Isolated Grounded Systems, confirms the requirement for a single grounding system, even for isolated grounded systems. It states that the equipment grounding conductor for an isolated grounded system shall be connected to the equipment grounding bus at each panel board and at each motor control center. Similarly, Section 408.20, Equipment Grounding Conductors for Grounded Circuit Systems, reinforces the requirement for a single grounding system for grounded circuit systems. It mandates that equipment grounding conductors for grounded circuit systems shall be connected to the system grounded conductor or grounding electrode conductor at each service, at each panel board or similar distribution point, and at each motor control center. Section 250.110, Bonding of electrical systems, is also relevant, as it ensures that all electrical systems and equipment shall be bonded together and connected to the grounding electrode system in accordance with the NEC. This bonding requirement extends to isolated circuits, ensuring they are connected to a common grounding system. The use of multiple ground rods can create ground loops. Ground loops occur when there are multiple paths to ground, resulting in circulating currents that can introduce noise and interference into sensitive electronic equipment, such as PLC and Ethernet communication systems. This can lead to communication errors and unreliable operation. A single, properly installed grounding system ensures that fault currents are effectively distributed throughout the system. This reduces the risk of electrical hazards and minimizes the potential for voltage differences between different points in the system. Electrical safety is paramount. A single, properly installed grounding system provides a reliable path for fault currents, which helps to minimize the risk of electrical shock and fires. By adhering to the NEC grounding requirements and avoiding the use of separate ground rods for individual panels, a safer and more reliable electrical system can be achieved. When addressing Ethernet communication problems between PLC, focus on verifying the integrity of the existing system ground. Ensure that all grounding connections are properly made and that the grounding electrode system is adequate for the facility. Running separate ground wires from each panel back to the main grounding point can help to improve grounding performance, but it is important to ensure that these wires are properly sized and connected in accordance with the NEC. If noise is suspected to be the cause of the Ethernet communication problems, consider implementing additional noise reduction techniques, such as using shielded cables, installing filters, and separating power and signal cables. However, these measures should be implemented in conjunction with a proper grounding system, not as a replacement for it. Firstly, review NEC Section 250.4 for general requirements for grounding and bonding. This section provides the foundation for proper grounding techniques. Secondly, inspect and test the existing grounding electrode system to ensure it meets NEC requirements. This includes verifying the size and material of the grounding electrode conductor, as well as the resistance to ground. Thirdly, ensure that all metal enclosures and equipment are properly bonded together and connected to the grounding system. This helps to create a low impedance path for fault currents. Fourthly, use appropriate grounding techniques for sensitive electronic equipment, such as PLC and Ethernet switches. This may include using shielded cables, isolated ground planes, and surge protection devices. Fifthly, avoid creating ground loops by ensuring that there is only one path to ground for each piece of equipment. This can be achieved by using a star grounding configuration, where all grounding conductors are connected to a single point. Sixthly, consider using fiber optic cables for Ethernet communication to eliminate the possibility of ground loops and electrical noise. Seventhly, regularly inspect and test the grounding system to ensure it remains effective. This includes checking for loose connections, corrosion, and damage to grounding conductors. Eighthly, document all grounding and bonding procedures, as well as any modifications or repairs made to the grounding system. This helps to ensure that the grounding system is properly maintained and that any issues can be quickly identified and resolved. Ninthly, consult with a qualified electrical engineer or electrician to ensure that the grounding system complies with all applicable codes and standards. This can help to avoid costly mistakes and ensure the safety of personnel and equipment. Tenthly, provide training to personnel on proper grounding and bonding techniques. This helps to ensure that everyone understands the importance of grounding and how to properly maintain the grounding system. By following these steps, a solid and reliable grounding system can be established, which will help to prevent Ethernet communication problems and ensure the safety of personnel and equipment. Remember that the NEC is a minimum standard, and in some cases, it may be necessary to exceed these requirements to achieve optimal performance. For example, in areas with high levels of electrical noise, it may be necessary to install additional grounding electrodes or use more sophisticated grounding techniques. It is also important to consider the specific requirements of the equipment being used. Some manufacturers may have specific grounding recommendations that should be followed. By carefully considering all of these factors, a grounding system can be designed and installed that will provide reliable performance and ensure the safety of personnel and equipment. This includes reviewing equipment manuals to determine any specific grounding requirements, which is also important for a well-designed and functional grounding system. Furthermore, consider the environmental conditions in which the equipment is operating. For example, in areas with high humidity or corrosive environments, it may be necessary to use special grounding materials or techniques to prevent corrosion and ensure the long-term reliability of the grounding system. This also means that if there are significant changes to the electrical system, such as the addition of new equipment or the relocation of existing equipment, the grounding system should be re-evaluated to ensure that it continues to meet all applicable requirements. Ultimately, the goal is to create a grounding system that provides a safe, reliable, and effective path for fault currents, while also minimizing the risk of electrical noise and interference. This requires a thorough understanding of the NEC, as well as the specific requirements of the equipment being used and the environmental conditions in which it is operating. Section 250.6 of the NEC covers the requirements for the grounding electrode system. The grounding electrode system is the means by which the electrical system is connected to the earth. This connection provides a low impedance path for fault currents to return to the source, which helps to protect people and equipment from electrical shock and fire. The grounding electrode system must consist of one or more of the following electrodes: a metal underground water pipe that is in direct contact with the earth for at least 10 feet, a metal frame of a building or structure that is grounded to the earth, a concrete encased electrode that is at least 20 feet long and is encased in at least 2 inches of concrete, or a ground ring that is at least 20 feet long and is buried at least 2.5 feet below the surface of the earth. The grounding electrode system must be connected to the electrical system by a grounding electrode conductor. The grounding electrode conductor must be sized in accordance with NEC Table 250.66. The grounding electrode conductor must be installed in a manner that protects it from physical damage. Section 250.28 of the NEC covers the requirements for bonding. Bonding is the process of connecting together all of the metal parts of an electrical system. This includes the metal enclosures of equipment, the metal conduits that carried the wiring, and the metal grounding conductors. Bonding helps to create a low impedance path for fault currents to return to the source. This reduces the voltage in the metal parts of the electrical system, which helps to protect people from electrical shock. Bonding is required in all electrical systems. The bonding jumpers must be sized in accordance with NEC Table 250.102. The bonding jumpers must be installed in a manner that protects them from physical damage. Section 250.96 of the NEC covers the requirements for equipment grounding. Equipment grounding is the process of connecting the metal enclosures of equipment to the grounding electrode system. This provides a low impedance path for fault currents to return to the source. This helps to protect people from electrical shock and fire. Equipment grounding is required for all electrical equipment that is likely to become energized. The equipment grounding conductors must be sized in accordance with NEC Table 250.122. The equipment grounding conductors must be installed in a manner that protects them from physical damage. Section 310.15 of the NEC covers the requirements for conductor ampacity. Conductor ampacity is the maximum amount of current that a conductor can carry safely without exceeding its temperature rating. The ampacity of a conductor depends on the size of the conductor, the type of insulation, and the ambient temperature. The NEC provides tables that list the ampacity of different types of conductors. The ampacity of a conductor must be selected so that it is large enough to carry the load current without exceeding its temperature rating. Section 314.16 of the NEC covers the requirements for box fill. Box fill is the maximum number of conductors that can be installed in an electrical box. The box fill requirements are based on the size of the box and the size of the conductors. The NEC provides tables that list the box fill requirements for different types of boxes. The box fill must be calculated to ensure that the box is not overfilled. Overfilling a box can cause the conductors to overheat, which can lead to a fire. It's important to remember that the NEC is a complex and constantly evolving document. It is essential to stay up to date on the latest changes to the code to ensure that your electrical installations are safe and compliant. The best way to do this is to take continuing education courses and to consult with a qualified electrical inspector. Electrical safety is a serious matter, and it is important to take all necessary precautions to protect yourself and others from electrical hazards. Finally, always remember to de-energize circuits before working on them. This is the most important safety precaution you can take. Use a voltage tester to verify that the circuit is de-energized before you begin working. Wear appropriate personal protective equipment, such as gloves and safety glasses. Never work alone. Have someone else present who can help you in case of an emergency. If you are not comfortable working on electrical equipment, hire a qualified electrician. Electricity can be dangerous, and it is important to take all necessary precautions to protect yourself from electrical hazards. Proper grounding is essential for electrical safety. Grounding provides a path for fault currents to flow back to the source, which helps to protect people and equipment from electrical shock and fire. Make sure that all electrical equipment is properly grounded and that the grounding system is properly maintained. By following these tips, you can help to ensure the safety of your electrical installations.